Okay, it's time, so let us get started. So it's a real pleasure to have Professor Maylee Sanchez from Florida State University today talking about neutrino physics and especially looking at the future called DUNE experiment. So Maylee was originally from Venezuela. He finished his college degree in Venezuela and came to the United States afterwards to Tufts. And she has done such an amazing work as a grad student on Sudan DUNE experiment. We in Berkeley tried to hire her as a postdoc, and she turned us down and instead went to Harvard. And then eventually rose very quickly to a senior staff in Argon and kept moving around to Iowa State University, now at the Florida State University. And she's been leader in neutrino experiment in this country. And especially more recently, that she's been working on an experiment called NOvA that sends a beam of neutrinos from Fermilab to a site in Minnesota. And they actually, in some sense, compete or complementary to another experiment in Japan. And they got together and worked out a joint analysis of two experiments, which was a very difficult thing to do because, different collaborations of different cultures and different issues of systematics, different detectors, and different attitudes even you mentioned to me. That was very interesting. But she managed to overcome those barriers and came up with a joint science paper recently, actually this year. So that was quite an accomplishment. And she has numerous awards. She's been an APS Fellow. She got an Early Career Award. And she's been actually on a distinguished Wyatt Green Professor Chair at Florida State University. And she was also working with me together on the P5 panel, the Particle Physics Project Prioritization Panel, which actually recommended the next 10 to 20-year program of the U.S. particle physics to the government. And she was very instrumental on this panel. And I have to say that if any of you found our paper, rather our report compelling, that is largely due to the writing skill Maylee contributed to the report. So I'm very impressed by that as well. And let's see, what else do I add? Yeah, and also when the colloquium committee contacted me to suggest somebody working on DUNE experiment to talk about it, they initially suggested somebody else, a spokesperson actually, but I said, no way, it has to be Maylee. So there she is, and accepted the invitation. So she's speaking to us about this future opportunity, current ongoing experiment, as well as future opportunity in neutrino physics. Okay, the floor is yours.
All right, thank you, Hitachi. Anyway, thank you for that very warm introduction. I really appreciate it. And anyway, those P5 days, as hard as they were just good times. And thanks to your leadership for that. All right, so I'm here to talk to you about the DUNE experiment, but I'm going to talk to you about long baseline neutrinos more in general. And so the title of my talk is how do you, unveil or unravel the mysteries of the universe by detecting neutrinos. So hopefully to convince you that experiments like DUNE and its predecessors such as NOvA and T2K can help us do that. All right, so I'm going to start at the very basics, counting on the fact that we have a broader audience and not just particle physicists. So the first question you might ask is, what is the universe made of? And we know we have quarks and electrons and neutrinos, right? And we have more than one set of them. Thank you. That looks better. Yes. And we have more than one set of them. And this is, a little bit like the periodic table of particle physics, right? So we have, see if I can do this with two hands. We have, am I doing that right? Yeah, no. Yes, okay. All right, so this is, the sort of the periodic table of particle physics, so that we call that the standard model, and it has the description of, the quarks and the leptons and the force carriers that, help do the interactions between the particles. And if you noticed, you've been paying attention to last sort of decade, you know that there's one piece missing here, which is a special particle called the Higgs, right? So that missing piece of the puzzle. And it is, I update this every time I give my colloquium, so it's now 12 years ago that we had sort of the biggest news in particle physics in a while, right? And it made, if you were not paying attention to physics at the time, it really made the headlines on the 4th of July of 2012. And it showed up, in the news across the world as there is this really big deal. And it took us to this moment, which I really love that picture where, Fabiola Gianotti is the sort of the experiment representative here, and Mr. Higgs himself is sort of the representative of the theory. And it's this moment where you have had this prediction of theory for so many years that has been now confirmed or demonstrated by experiment. So I go back to that moment when I look for inspiration into the connection between theory and experiment. All right, so in principle, the standard model is complete. And at the time, Twitter said it. Now we know better, right? Don't believe everything you see in Twitter. Or X, as you guys might know it these days. But what you would do in 12 years later is ask ChatGPT if the standard model is complete, right? Isn't that what we do these days? Don't ask Twitter. OK, so I have done that. And you can ask, the Higgs particle has been found. Does that mean the standard model is complete? And actually, that counts as a forceful no from ChatGPT, right? And it tells you that, and then with some caveats, it doesn't want to offend anybody. So it is a monumental achievement to have discovered the Higgs boson. It does not mean that the standard model is complete. While the standard model is a highly successful framework, as we all know, for describing all of the known particles and their interaction, it is not the final word on our understanding of the universe. Completely agree with ChatGPT, yes? And here's why. And it even will tell you what are the missing pieces of the standard model. Okay, and the case that I'm trying to make to you today is that neutrino masses are indeed one of those crucial pieces that we need to understand better, right? The standard model, and here's where I disagree with ChatGPT, predicts the neutrinos to be massless. Well, I don't know that the standard model really predicts the masses of anything, right? However, we can get away with a standard model that in fact has neutrinos to be massless, and there are good reasons for that. We'll talk about it in a minute. But experiments in neutrino oscillations, such as Super Kamiokande and SNO, and now a long collection of other experiments I'll mention later, have shown that neutrinos do have tiny but non-zero masses. And therefore, that requires a physics beyond the standard model. And so part of the case that I like to make is that neutrinos are a good place to look for that physics beyond the standard model, because we know that they must be something that explains their masses. Okay? All right, enough with ChatGPT for the day. So one way you might want to ask this question is, why are neutrino masses that small, right? Or another way to ask that question is, why they don't like the Higgs so much, okay? And the short answer, spoiler alert, we really don't know. But we do know that particles that do have mass need to have right-handed partners, and neutrinos, as it turns out, do not have them, or we haven't observed them, right? And so my right-handed partner over here, it's gone. All right, so let me say that a little bit more clear. We do know that particles that do have mass, such as, say, let's pick our friend the electron, right? They change their handedness when they interact with the Higgs field, right? Remember, they don't really interact with the Higgs boson as such, but as the field that permeates coming from the Higgs. And so I need to be able to write that interaction, or write sort of a term that goes into my Lagrangian of the standard model. I need to write something that has a left-handed particle and a right-handed particle. And as it turns out, I have not observed a right-handed neutrino. I have observed, however, right-handed antineutrinos in nature, and similarly, I'm missing my left-handed antineutrino, and I'm missing my right-handed neutrino, right? So by not having right-handed partners, I would say most naturally do not feel like adding a right-handed partner that doesn't exist is a good idea at first hand in the standard model. So that's sort of what we mean by neutrinos do not have mass in the standard model. All right, so nonetheless, let's try an exercise. It turns out you could extend the standard model to have, to add masses to the neutrinos. And there is, however, a number of ways you can do that, and there's not a clear answer as to what is the right way. So let's say I could explain tiny neutrino masses a number of ways. Here's my three favorites. I'm sure the theorists in the room can come up with a whole collection of them that are not these. So one thing you could say is, well, neutrinos couple to the Higgs, but very, very weakly. So I have to put in some parameter in there that says this is very weak. And right-handed neutrinos are somehow secretly hidden from all of our experiments. Possible. All right, so different one is neutrinos coupled to a very different Higgs boson. That would be fantastic news for particle physics, right? And then there might be their own antiparticle. So I might write a term that has a left-handed neutrino and a right-handed antineutrino. It's a possibility, but it has to be a different kind of Higgs, not these other Higgs that we have observed. And then last but not least, maybe a favorite of mine, but other people might think differently, is neutrinos masses are small because there's some other source of mass out there, right? Not the Higgs, some other mechanism to give neutrinos to the mass, right? Which is a new energy scale directly responsible for them being small. And that's called the seesaw mechanism, and somehow a very heavy, represented here by this guy, a very heavy right-handed neutrino that cannot be observed. Maybe it was around at the beginning of the universe or something. Somehow explains the fact that the neutrinos that we do observe that are left-handed are very light, right? And just to give you a sense for let's say if my light neutrino mass is around 0.05 eV, then that mass scale would be something like 10 to the 15 GeV. And some of the reasons why this is appealing is that you can come up with a higher level symmetry that then breaks down to something that do this. So in a way, neutrinos will be sort of this special component of the model that is telling you about that energy scale. All right, so I'm going to claim that that's all good reasons to go and study neutrinos, and actually to go study the Higgs, right? And, this is in part sort of the motivation for some of this planning that came up in our planning exercise for the next decade that Hitoshi was a part of. And so last year, as Hitoshi mentioned, we worked in this P5, so-called P5 report. You can see sort of the news around it. I think this was sort of at the end of December on 2023. And the biggest news about this, if you look at it, is particle physicists agree on something. And I'm going to now claim for you that I bet you already know Hitoshi had something to do with this, right? In our meetings, we call Hitoshi the master of consensus, right? So you could get a room full of high energy physicists to agree on something, and now the community has been very welcoming of the report that came out of this. But I'm going to use that to cite some of the arguments then to go after neutrinos, right? So neutrinos, as we discussed, come in three types or flavors, and they undergo these phenomenon of oscillations that I'll talk about in a minute. And although the standard model can be augmented to accommodate neutrino mass and oscillations, right, we do not really know in which way, which of these, for instance, I gave you three of them, to extend the model, right? Wouldn't it be nice to know? And these different extensions give different predictions about the birth of the universe, and I'm not going to go into the cosmology of that. But I think that's a good argument to say that we must investigate the mysteries of neutrinos in order to explore these deep connections between their physics and the Standard Model. And that's a direct quote from the report. All right, so let me give you sort of a briefing of neutrino oscillations. So let's say I have a beam of neutrinos that I produce. And I start with a particular flavor, so I'm going to just do muon neutrinos here. And I let them travel a whatever distance, and at a certain distance, I see that these neutrinos have now changed flavor into tau, mostly tau neutrinos, but a tiny bit of electroneutrinos, as you will learn later. And that phenomenon is possible because if you go back to your basic quantum mechanics that you can do even as an undergrad, the flavor eigenstates are linear combinations of the mass eigenstates, right? And so I can then write a non-zero probability of detecting that different neutrino flavor, right, than the one that was produced at the source. And that probability has actually this very nice, simple form. I promise you I'm not going to show you the 3 flavor oscillation probability because that loses a little bit of the elegance. But here it is. I mean, it's a nice, simple idea. You have 2 parameters that are coming from nature that you would like to know. There's properties of neutrinos. One is the difference of the masses, right? So if the difference between the masses is 0, this is a sine square. You have no probability of this happening. So you really need the fact that you are observing this change in flavor means that you have massive neutrinos. And then the other one is, with what strengths do these neutrinos mix? Is that a little bit of mixing, or is that a lot of mixing, right? So those are the parameters of nature of the oscillations. And then that depends on what distance they have traveled and what energy they have. And these are your experimental parameters. And it turns out you can design experiments, right, that have variations in those, and they're able to measure these probabilities with quite a bit of detail. And so one question you might ask is, well, you have done this. Now I'm going to expand it to the 3 neutrinos, but I'm only going to show you the matrix that is sort of would go equivalent of here with a 3 neutrino mixing. Right? And so now we have 3 mixing angles and 1 phase. Right? As it turns out, that phase is what we know as the CP violation phase in the lepton sector. And then I'm going to ignore the Majorana phases of these, which you cannot measure with long baseline neutrinos. You would have to go and do, for instance, a neutrino-less double beta decay. All right, so each of these sectors have been, in fact, measured by several techniques. Going back into history, we observe neutrino oscillations with atmospheric neutrinos and solar neutrinos, as you might have seen in the Nobel Prize associated with neutrino oscillations. And since then, we have measured the same oscillations with, let's call them human-made sources, right? Not just natural sources. And the values are, here sort of the order of magnitude of the values. You will notice that one of the places where I don't have a number is that delta CP. Delta CP has not been observed in the lepton circular. And the kind of experiments that I work on and I'll talk about today look essentially at this sector over here, so have access to that delta CP that you see there. All right, so next question you might ask is how well do we know it? So the starting date of this plot is 1998, which is sort of nominally the discovery of oscillations. And the plot here comes from the community work that was done towards the P5 report. So the community got together and sort of reviewed the state of the field and made this very nice plot that I really like, because it shows you how much we have learned in these 20 plus years, right? We've gone from knowing delta m squared when I was a graduate student, which was just like basically we know what order of magnitude we live in, right? To a measurement that is 1.2%, Okay, that's, I think, a big deal and a reflection of the progress. And you have shown, I keep sort of pointing to the fact that each of these numbers have been measured more than one way, and that different kinds of experiments have access to those parameters, right? All right, so those are the things we know. So what don't we know? So as I said, CP violation in that lepton sector has not been measured. This connects to things like matter-antimatter asymmetry of the universe. So you certainly want to know that. Another one is the mass ordering. So if I take those 3 flavor eigenstates that I showed you earlier, and I put them in some ordering, of course, we have not given them very interesting names, so I'm just going to say, 1, 2, 3. As it turns out, this delta m squared, which corresponds to the neutrinos that originally, at least, the neutrinos, to the oscillations you see from neutrinos coming from the sun, or even sort of in reactor neutrinos, it turns out that we know that 2 is above 1, okay? But instead, for this number 3, we, somewhat biased, write it at the top. But it turns out we have not measured that. So this state number 3 could be here in what we call normal mass ordering or mass hierarchy, or it could be below, and that would be inverted mass ordering, okay? And so you would like to know that. And then the octant of the large mixing angle, and so the mixing angles are reflected in this graph by the amount of each of the flavors that each of these mass eigenstates contain, right? Remember I said they're a linear combination. And so it turns out that the angle that tells you about how much nu mu and nu tau lived in that mass in the third eigenstate is something that we don't know. It looks like it's close to maximal, but we don't know if it's maximal or something slightly different, okay? And it certainly impacts, because we do these measurements in experiments that have all of these different parameters, it turns out that that uncertainty impacts also our knowledge of the others, okay? Now, we can observe these or make these measurements in things like reactor accelerator and nanospheric neutrino experiments, so that's a plus that we have several types of experiments where we can do that. The other thing you might want to ask is how well do we want to know it? Okay, it was like, when are you going to stop doing long baseline neutrino experiments? And one of the things that is underlying this is that we have what's so-called a 3-flavor neutrino paradigm, right, in which we can write and measure each of these parameters here, right? And I have sort of titles for different experiments that had measured each of them, right? And what you eventually want to do is you want to measure each of these elements in the matrix with more than one technique to paint a full picture and really stress test the picture of 3-flavor neutrino oscillations. And you can even sort of ask questions about, for instance, unitarity of that matrix, okay? And here I show you, these plots here come from a global fit done of all of the experiments out there, trying to do one, and this is sort of one of 3 leptonic unitarity triangles of that missing matrix, imposing the unitarity condition. And so that tells you sort of where we're at right now. This is from 2016. Here's 8 years later. You can see the sort of improvements, again, that the field is making as we make these experiments. And in fact, I had this plot here from new fit 5.3, new fit 6 came out about a month ago. And so in 2024, I have an update to that. And what you can see is that there's enough uncertainty, for instance, in here, that this thing moves around depending on the little bit of data that you add to the system. So we still have work to do, right? Ideally, you want that sort of better constrained. Okay, so I think I've given you, hopefully, a picture of why we want to study neutrinos. So now let me explain how we study them, in particular using the kind of experiments that I work on. And so what we do is we produce neutrinos with accelerators, right? And what we do is we use protons from an accelerator, as I guess you will look at it here. and impacting a target that will produce pions and kaons. And these mesons get focused with this focusing horns system that will allow you, in a way like in an optical system, choose the energy of the end sign of the mesons that you want to select. And then you allow those mesons to go through to decay into, in this case, mostly muon neutrinos with a tiny little bit of an electroneutrino component. So you can see what kind of spectrum you get out of that. So if I sit on axis of that beam line, I get sort of a broad spectrum that you can see here. This is actually for the NOVA experiment. And if you look at the oscillation for this particular, for the particular distance that the NOVA experiment sits on, you can see that it turns out the oscillation sits much lower than the on-axis beam. And so what you do, having that beam was actually constructed for Minos. So what the NOVA experiment did was to build sort of off-axis, and the kinematics of that, the decay kinematics, allows you to select a narrow band spectrum. You can see how the NOVA off-axis angle gets selected so that you're at the maximum of this oscillation, or close to the maximum of that oscillation, so that you are very better able to study the oscillation. So that's sort of the principle of on-axis and off-axis experiments. And so if you were designing your own long baseline experiment, you will want to then decide, as I said earlier, your baseline and your energy. So find a detector location at the right distance from your source in order to see that oscillation phenomena. You will want to make the beam as intense as possible. Neutrinos are very rarely interacting particles, and so you want to have as much intensity as you can. The US program has been a leader in the beam intensity, with NOVA having 700 kilowatts, and as you will see, DUNE keeps pushing that challenge well beyond that number. Detector mass, depending on your event rate, you want to build a sufficiently large detector. Japan's program has led in terms of detector mass. They had the super Kamiokande detector is 50 kilotons. Hyper Kamiokande would be larger than that. And then you want to decide what kind of technology you've used in your detector, right? And depending on your detector technology, your background rejection, your uncertainty control might be easier. All right, so I am going to use, and this is a little bit of a detour in terms of DUNE, but I'm going to use the current state of the art, which is the NOVA and T2K experiments, to give you a sense about why you would want to move on to DUNE. Okay? So there are two running experiments on long baseline experiments using neutrino beams, one produced by accelerators, one in the US. At the new beam at Fermilab runs north to northern Minnesota. And there, before, we had Minos right on axis, and then NOVA was built 810 kilometers away, literally sort of the last place where you could build something that was not in Canada. It's one way to think about it. And then instead, T2K is sitting in the one edge of Japan. And then, as it happens, the magically has the baseline from an accelerator on this side called JPARC to actually then study the same phenomena, right? So you're looking for this L over E at around 500 kilometers that allows you to study that oscillation in the atmospheric neutrino range. All right, so with that sort of setup, what you want is your precision is achieved by placing a detector close to the source, right? We call those the near detector. And then one at or close to the oscillation maximal that we called the far detector. And ideally, the measured spectrum in the near detector is then used to predict what you would observe in the FAR detector in particular, because you're able to measure these without oscillation, so that's your control sample, and then that allows you to cancel out many of the things like flux and cross-section combination so before considering oscillations. Okay? The kind of signatures that you're going to be looking for is then things like mu neutrino disappearance. So as I showed in the oscillation description I had earlier, you start with a beam of mu neutrinos and then figure out how many of those neutrinos might have gone away. And then you look for the appearance, and in particular, the appearance that we're going to look for is the electroneutrino appearance that allows you to measure that tiny little angle that appears in the nu3 state. Okay, so using these two experiments, let me just give you some more characteristics about that. Might be useful later. Here's sort of the difference between T2K and NOVA. The T2K beam peaks at around 0.6 GeV. The NOVA beam peaks just below 2 GeV. And these different neutrino energies lead to different neutrino, or being dominated by different neutrino interactions. So T2K is primarily quasi-elastic interactions, as you're sort of living in this region down here below the 1 GeV. And NOVA instead has let's call it a healthy mix of quasi-elastics and 2P2H resonant and deep inelastic interactions, right? And that said, NOVA is a calorimeter, and so you were able to reconstruct things that come out of the neutrino interaction that are not just the lepton, whereas that is harder to do in a water Cherenkov detector. So these two, significantly different experimental setups. I'm going to, again, do that in parallel for you so that you can see what different experimental designs gets you. So if you look at these plots here, I'm looking at the probability at the top of nu mu's going to nu e's, right? This is the interesting probability because it's associated with that small mixing angle, but in particular is where the CP term would appear. And what you will see is that if I look at the top and at the bottom has the antineutrino equivalent of that. For something like normal ordering, you can see that the blue appears here at the top, and the orangey, which is the inverted ordering, appears at the bottom, and that for antineutrinos, that reverses, right? Similarly, if you were looking for your CP phenomena, you will see, and this is a little bit harder, I'm sure, to see from where you're at, but there's a black line where the delta CP sort of, if delta CP is 0, appears here, and then the two other extremes are the sort of two maximal points of that delta CP, and those again sort of invert from one to the other. Now, it turns out that matter effects help you, particularly with the mass ordering. So when you go to NOVA that has a longer baseline, those differences are more stark, right? So you can see the difference between the orange and the blue much better in NOVA. This makes that, in fact, that effect is on the order of, it's 9% for T2K, but it's actually 19% for NOVA. And instead, whereas the CP effect is sort of equivalent between the two experiments. So these two experiments are actually pretty complementary. The T2K isolates more of the impact of the CP violation, whereas NOVA has a significant mass ordering sensitivity because of those differences. All right, so let me show you what is more or less sort of the state of the art in the sense that these are recent results from NOVA and T2K. This is 2020 data. For those of you who care, both experiments have released more recent results, but we use these particular data sets in the combination, and so I'm going to go with that. It hasn't changed that significantly, okay? So what you will see in this plot is now I'm showing you the sine square of theta 2,3, right, against what my CP violation parameter is, yeah? And I showed you that for the normal ordering at the top and the inverted ordering at the bottom. And the normal ordering at the top has these blue areas, which are sort of NOVA results, okay? Whereas the T2K result is in black, right? And the thing that would sort of jump out at you is that there is a difference between the favored CP from each of the two experiments. This is, at the 90%, so it's a very mild disagreement, right, on these allowed values. You can see that, however, for instance, in the inverted ordering, we're sort of more on the same region of space, and both experiments mostly agreed that these are, this region here is excluded. Given these results, there's also a lot of interest in combining it, and apart from the results, it's like you have these two, the best data sets out there on this particular set of parameters. Can you do the work to combine them and get a better result? So we've spent, as Hitoshi alluded earlier, a good part of the last 5 years or so trying to do that. And so I'm just going to walk you through the results and not give you any of the details about how we actually did this analysis. As it turns out, the experiments individually have preference for normal ordering. Okay, but that means that in these, when I do these, this fit here is preferred over this fit here, right? So my best fit, my little crosses or dots, leave for both experiments in the normal ordering. But as it turns out, they don't agree very much. So when we do the NOVA joint fit, you end up with a weak preference, and you can see how weak it is here, right? That's a 58 to 42 posterior for that inverted ordering. And I'll say, in addition to that, that it turns out that if you take the delta m squared as a constraint from Diabay, you reverse the mass ordering preference back to normal ordering. So that's actually a pretty fragile result, and I wouldn't take anything from it that we have measured or decided what the ordering is. You can see what I just talked about when you look at the individual experiments, right? So NOVA prefers normal ordering at the 67 to 33%. T2K prefers it at the 81 to 19%. As soon as you combine them, you get this 58 to 42 posterior, and you can see it that these are higher than this, and that this is the highest once you do the combination. And all it's going on is that the fit is preferring the place where the two experiments sort of agree the most versus the other piece. All right, and then you can see, again, in terms of CP, what do we learn out of CP? And you end up with, this delta CP pi half getting excluded at the 3 sigma credible interval for both mass ordering. So that here you have, profiles independently for normal, independently for inverted, but when you do the combined, you still end up excluding that. So this one seems robust, that rejection. But it doesn't tell you about excluding 0 yet, right, for instance, which would be an interesting result. And so again, it's just like a slightly different way to show you that. Again, I showed the individual results in the lines, and then the shaded area is the combined result. So what I want to point out to you, so that I move on to why we want to do DUNE, is that this is the state of the art in 2024. Okay, so we have made a lot of progress, right? The delta, we have gotten to this delta m squared that is, that is a really good measurement. The other parameters have improved, but when we're looking at these parameters that really, are sort of the next thing that we want to learn, we're not quite there yet. Okay. So in that context, do you want to make a better experiment? And the next generation long baseline experiments then are being planned with higher intensity beams, larger mass to collect more neutrinos, higher detector resolution, and other techniques for better background rejection and systematic uncertainty control from the detector, the flux, and the cross-section. And just like before, 2 complementary programs are happening in the US and Japan. with, again, these very long, very different baselines where you have what we've done in the US is planned for something that has even more matter effects that really enhances that mass ordering difference, right? And allows you to disentangle the ambiguities between the CP and the mass ordering much better. The other decision that is different is that with DUNE, we have gone with a broadband beam, and hyper-K is still off-axis, right? It's still using the same relationship as before. All right, so now I'm not going to talk about hyper-K in any detail. I'm going to tell you about DUNE, as promised. So here's what the DUNE experiment is in a nutshell. It's a baseline of, as it turns out, 1285 kilometers, almost 1,300, depends on what you like to remember better. The beam power is so much higher. It's now over 2 megawatts. And the excavation of the far cavern has been completed, and it's planned for 40 kilotons detectors in 4 modules, divided in 4 modules, so 10 kilotons each. Here's a picture of that completed excavation of far cavern. And again, some of you who have been in all of these discussions in the past about being able to have an underground, a large underground lab in the U.S., now such thing exists. And so it's a big, I think, success to being able to build that. I'll talk a little bit about the plans later, but the idea is you'll have a first far detector around 28, and the beam and the near detector for the long baseline piece of these in 2031. DUNE is a collaboration of over 1,400 scientists. So it's a pretty large international collaboration with scientists from Europe, all of the Americas, right, and elsewhere. All right, so let me go back to, you now know you need these 3 components, right, to these long baseline experiments. So let me stop by the DUNE neutrino beam first. That's called the LBNF, Long Baseline Neutrino Facility Beamline. And that's going to be constructed at Fermilab. And again, here in this picture, a little bit blurry picture, but the current setup uses the main ejector to essentially shoot a beam north of that plot going to Minnesota. And now you're going to create a beam coming out of here that instead goes west towards South Dakota, right? And actually western South Dakota. And some of the upgrades required to take that beam, we talked about that 700 plus megawatt beam kilowatt beam that you have for NOVA. It's being upgraded to 1.2 megawatts to a program that's called PIP2, Proton Improvement Plan, and then doubling the frequency to that gives you that extra 2 megawatts. The thing to give you a sense of the improvement that it represents over the current set of experiments, here I have the plot for NOVA, right? You might recognize the little peak just around 2 GeV. And you can see that the DUNE peak at 1.2 megawatts, right? It's this large peak over here, okay? And one of the key things that is now you have these large statistics, this is one argument to have gone now broadband as opposed to narrowband, is that it covers the first oscillation maximum, right, as you would see here, and you have statistics even at the second oscillation maximum and even at the minimum between the two, right? So you now have statistics that span the first and second oscillation maximum with much better statistics than we had before. And then you can also see in this plot, so now I have my neutrinos on the left and my antineutrinos on the right. And these are both for normal ordering, right? So you can imagine that for the inverted ordering, these actually flip. But for the normal ordering, here's the difference between the values of delta CP, right? And so you can see, for instance, for my maximum here, this is minus pi half, and this is pi half, and the other one is in between. And you can sort of similarly see those inverted, right? So the purple here corresponds to the same as the purple over here for the anti-neutrino, right? And you can see how that effect is also sort of seen in that oscillation maximum. So by having a broader beam, I now be able to measure and hopefully characterize those differences much better than the current generation of experiments can do. All right, so the other aspect you want to think about is what are we using for detector technology. And as it turns out, DUNE is based using modular liquid argon time projection chamber technology, and for the first time in these very, very large detectors. And you can see liquid argon pictures are just always sort of stunning. These are actually simulated images. But here is a 3GeV muon, or muon neutrino, right, coming into sort of the side of the screen and producing a muon that you can clearly see going through here, and a hadronic shower as well as what's probably a proton over here. So you can see that the distinction between that and, say, an electron neutrino that produces an electron shower instead of a muon is actually pretty easy to the eye. So these detectors have excellent imaging capabilities, excellent energy reconstruction capabilities. It has distinction. Not only can you do electron to muons, you can even do electron to gamma separation. It has low thresholds for charged particles. In fact, you see so much more of the hadronic interaction that you ever seen. And the other point that I will make is this modular technology has enabled experimentation with multiple types of readouts. For instance, the first DUNE model is planned to be a horizontal type drift, whereas the second module is a vertical type drift. And so there's improvements and learning lessons as we go by the fact that you have a modular technology. All right, so I've talked about the beam, the FAR, what the FAR detector, and it turns out near detector technology is, but sort of the detector technology. And now let me mention the DUNE near detector. So the goal, as we talked about before, of the near detector complex is to enable having a prediction of that, what I'm going to see in the FAR detector spectra, right? And there is, these in many of the experiments that we do today, there is this uncertainty because you have this product of the flux and the cross section that you're measuring at the same time in the near detector. One of the ways that DUNE addresses this, and this again is sort of being done for the first time, is that the near detector being built that includes a liquid argon detector and a spectrometer is going to be movable. Okay, and by being movable, as we learned before, things that you can do, moving off axis. When you're on axis, you're seeing sort of that broadband spectrum, but as you move off axis, you sort of are narrowing this beam at different energies, right? So you're doing energy selection by moving the detector off axis. And so now you can decouple or disentangle this cross-section from the flux to first order. The things that do not change as you move in energy are, sort of your cross-section, whereas the thing that is changing is the flux. So that will give you, again, a capability of actually making your uncertainties in, the flux versus the cross-section much smaller. Okay. Now, the other idea here is, okay, here we go. This is a very high rate environment, and as it turns out, liquid argon detectors are actually very slow. So that very high rate at the near side motivates doing modularity to smaller. So one thing that you can do is just divide your detector into smaller pieces so that the drift is actually shorter, because you don't really want to be dealing with all of these in a single list. It all becomes a blur. And the other is pixelated readout, which is something that is being led here at Berkeley, a Berkeley lab. So that's being tested in a series of prototype detectors that has actually been built and commissioned recently for DUNE, which I unfortunately don't have much more time to talk about. All right, so with those three pieces, those three components, let me just show you what the DUNE far detector spectrum would look like, right? And so this is now, before I was showing you just plots of the flux, but now, as you have the reconstruction and the actual statistics, you will be seeing, and again, this is sort of here on the left, I have sort of what is the normal ordering for neutrinos, and I have the black crosses here are for delta CP equal to 0, and the other ones are sort of the other extremes of the CP. And you can see again that when you do the antineutrinos now, you have flipped for the same hierarchy. You have sort of flipped the delta CPs, right? The red and the blue. And so what you're seeing is that for the CP violation of minus by half, for instance, DUNE sees an enhancement of nu-E appearance and a suppression of antineutrino disappearance. Okay, and so that's the key signature you're looking for when you're searching for that. And as it turns out, it's not, that is sensitive to all of these parameters, which give you different shapes in L over E, right? So as you increase in statistics, you're going to be able to see those shape differences, and this provides you additional handles to resolve the degeneracies. And similarly, if you add here, if this is for the mass ordering, if it's normal, it's now in red, right? And if it's inverted, it's now in blue, okay? And now you can see how striking that difference is between the normal ordering. And I think in this particular graph, this is selected actually for a delta CP of 0. The other variation that you're seeing is the variation of that angle, of that large mixing angle, right? So you'll be able to tell if you're at the maximal or at that other smaller, at the other extremes of some of the currently allowed region. So again, if new physics is present, there might not be a combination of parameters that fits the data, and it would give you at least a hint that the three-flavor framework might not be enough to describe the data. Okay. All right, so I have given you a little bit about what we feel like, what DUNE might be like once you actually do have data. All right, so at the end of the day, you can do these if you accumulate enough data to do it. So let's turn out what that sensitivity will be. And so for the best case scenarios, DUNE has better than 5 sigma mass ordering sensitivity. So that's sort of this plot out here, which this is, let me just walk to you. This is sort of in terms of years of data, okay? And you can see that you can get into 5 sigma essentially within the first year of data. And that's given by the fact that we're playing with those much larger matter effects from the longer baseline than, for instance, the current generation of detectors. And then for CP on the right-hand side, you can see how you progress sort of within 3.5 years, you can get to 3.5 or so sigma CP violation. That is for a particular value of delta CP. That's sort of the optimistic, larger values maximal value of delta CP. If you are in a sort of a broader, you can also ask the question for what would it take for 100% for any value of delta CP to be 5 sigma, right? And so now you are sort of 2.5 years in or so for for that in mass ordering. And for the CP, then you do have to sort of extend the amount of time towards the end of the program. You'll be able to do that sort of 3 sigma for something like 75% of the space. All right, and then the other question you might ask is, how well can you measure the CP violation if you see it, right? And so that's sort of in the order between 6 and 16 degrees, right? Now that's all we talked about is what happens, if physics is, what we imagine within the 3-flavor violation, but you also want to be testing things that are outside, right, beyond that 3-flavor oscillation effects. And so things that you can do are, of course, for instance, a sterile neutrino. For example, DUNE covers a wide range of the L/E at the near and far detector locations, right? And so in this plot, for instance, the standard oscillation is in black, and then the signature you would see within a sterile neutrino is something like that red line. So clearly you would see, for scenarios of steriles, you would be able to, again, distinguish that from standard oscillations. You could look for CPT violation that would show us difference in the parameters for neutrinos and antineutrinos, so having that capability of being able to see the two. And then also non-standard interactions with matter could give rise to different effects between DUNE and hyper-K, but also you can improve the bounds, the current bounds by just significant amounts in some of these parameters, depending on what your favorite NSI might be. And then last but not least, there are supernova neutrinos. So the DUNE experiments could also see thousands of neutrinos from the galactic supernova bursts. DUNE is sensitive to a different type of neutrino than other experiments, right? We're not seeing the neutrinos by inverse beta decay, which is what Super K and Juno would do. And so that enables the study of the core collapse mechanism and the supernova evolution. And in particular, DUNE is able to see the neutronization burst, right, in the part as part of that evolution of the supernova, and determine also neutrino mass ordering from this data, right? All right, and then last but not least, because I know that this is always a question at the end about when is all of this going to happen. So let me tell you a little bit about, and this is very much DUNE jargon. So DUNE is being built in 2 phases. So phase 1 is on track to construct the full sort of near and far side facilities that I've talked about. 2 10-ton liquid argon TPC modules. As I said, the caverns are built, right, and are being enable the installation of the detectors. And then you can build 2 of these large TPC models. The upgrade to 1.2 megawatts of the neutrino beam line is also in progress with the PIP2. And that movable large CPC that I talked about with also a muon catcher it's planned, as well as an on-axis detector that I really didn't talk about, but I think if you're moving your off-axis, if you're moving one of the detectors off-axis, you want to still be monitoring what happens on axis, so this detector offers that. And completing phase 1 is the highest priority in the P5 report, right? That's the recommendation. Apologies for the little, sort of text, but it is really literally copy and paste of what we took out there, right? So this is the first phase of DUNE, and PIP2 would open the area of precision of neutrino measurements that include the determination of the mass ordering. So that's sort of enabled by that recommendation. And then DUNE phase 2, which consists of 2 additional 10-ton modules, a beamline upgrade to 2 megawatts through the ASMERT upgrade, and a more capable near detector, of which I didn't really talk, but this is a gaseous argon TPC that would replace the muon spectrometer that is being built right now. The P5 report endorsed the 3rd detector, the ASMERT and the NDGAR in the next decade, right? And recommended to conduct R&D efforts to enable a fourth module with a broader physics scope. Okay? And these words come from, yes, I'm almost done. These words come, again, directly from the report. So in that context, DUNE it's pretty busy planning, a lot of these other things, and in particular for the FAR detectors, in a way, as you build these very large detectors, you sort of use the lessons learned from the ones that you've already built to do improvements in the ones that you're adding as you go along. So very naturally, for instance, the third module is being planned to be a vertical drift module, and with improvements to things like the light collection system and so on. And then the fourth module is something that has been called the module of opportunity, and it's called again that in the P5 report, where again more ambitious designs are being considered. And again, the recommendation there is to expand the physics that can do again beyond the things that I mentioned. And so there's different prototypes for different readouts, including the pixelated readout, integrated charge light readout, low background modules. Again, some of these things are being worked at here, I think Dan, right? And also non-liquid argon technologies such as TEA, that is something that Gabriel has been leading here at Berkeley as well. So those are all ideas out there, and it's a sort of an opportunity to think about, this is a facility that has a lot of potential in time, and we can start thinking about how to use it and how to add physics to it next. All right, with that, I hope that I convinced you that the future neutrino oscillation experiments is very bright, and that we have made very much, a lot of progress in the past decade. But the current experiments, and I work on one of these, so I am telling you that even if you combine the two best data sets in the world, right, you still have a somewhat blurry picture of nature. So one thing that makes me really excited is that by the start of the next decade, you're going to have multiple major neutrino experiments. I'm hoping this is like a golden age of neutrino physics. You have DUNE, you have Hyper-K, and they have Juno, which is a reactor experiment I didn't really talk about today. And DUNE is on track to produce significant results and contribute to these. One of the things, and I hope that I also convince you of that the complementarity of these experiments is it's really a plus, right? Yes, we are competitors, but in another way, you really do want to measure these parameters in more than one way, right? And you can only hope for mysteries that really are telling us about new physics. And we're entering, a precision era of neutrino physics with it, exploring what I feel is an area where we're bound to find clues for the physics beyond the standard model. And with that, thank you for having me.
Thank you, Mary, for making the subjects very clear and accessible. Let me first take questions from students in the audience. Any questions? No? That can't be true. I'm sure there are questions. Okay, let me open up to anybody in the audience. There.
I'm curious if we know yet what the rough mass scales are for the mass differences?
So do we know what the mass scales are? Yes. So the number for the new sort of, if you go from the doublet to the new 3, right? It's the mass square difference is about 10 to the minus 3 eV square, and then the other one, the one that comes from the solar measurement and the reactor measurements, in the order of 10 to the minus 5. Roughly speaking. So we have, very good measurements of that difference of the mass squares. We don't have a measurement of the absolute mass, right? And that's a different kind of experiments that can do that.
Just curious, DUNE, is there any possibility
Sorry, can you say it again?
Sorry, the high energy solar neutrinos with DUNE. I'm just curious, since you didn't mention.
Right, so that's, yes, so that's something that is being explored. And again, I think what some of the things that you want to do is, learn from lessons of maybe the first module to make sure that you're building that possibility into your program. So it's actually being actively pursued that you can do that. And then also proton decay, it's, there are some modes that can be done in liquid argon that are different than the ones that you would be able to do in a large experiment at hyper K. But again, I think you win for proton decay, you win with mass. And so you really have to look for things that are very specific. Like in the case of I think the supernova one is a sort of a really interesting place where you can show the complementarity right away between the two techniques. Thank you.
More questions? Yes, Dan.
You show this kind of tension between GDK and NOVA results that seem to prefer different spaces, but then when you do a joint fit, they kind of shift around significantly. Do you have a personal hypothesis as to what origin of this tension?
I mean, so I don't want to overstate the statement of the tension, right? I think these things, if I'm showing you 90% and claiming attention, you should, like, I don't know, like, make me walk out of the room. But we do prefer different, different parts of the space. And well, okay, so one way to think about this is T2K's result. I don't want to say that. Here's my bias, fluctuated to a place where you are really, so so one way to re-say that is that the model was not very compatible with T2K's antineutrino data, right? So they were seeing less antineutrinos than they should have seen, right? And it's a world of low statistics, so it looks, it could have been a fluctuation. I feel like they're more recent data sets, and it's something to pay attention to. It looks a little bit like they're reverting and getting closer to the model, right, to what you would expect on what is maximal CP maximal. But they looked they wrote this sort of Nature paper. It wasn't quite a discovery of CP violation, but like a 2 sigma. Right, away from zero, and but it comes from their antineutrino data not being actually very compatible with the maximal CP, maximal normal ordering that you can do. The NOVA data instead, again, perfectly possible. It's a fluctuation. I don't claim that one is a fluctuation and the other is not. The NOVA data instead leaves in a place where both the normal ordering or the embedded ordering could be possible because it's sort of, sorry, I'm trying to make here. So if you think about our ellipses that we like to draw about this, right? And this is the inverted ellipse, and this is the normal ordering ellipse, right? In NOVA, they touch. And in DUNE, they're much more separated. But in NOVA, they touch. And so the data of NOVA has ended up in this region with the 2 ellipses, right? And so we can be maximal. We can be maximal in one ordering or the other, and we're still compatible with 0, right? Whereas the T2K data, particularly the antineutrino data in T2K, wants to really exclude 0 because they're farther away from that sort of non-CP violation. Whereas in the case of NOVA, you are compatible with 0, and also sort of in this world where yes, you could be on the maximum CP, but not the same CP as T2K, right? And I don't know. We just ended up in 2 different places. There's one experiment has significant amount of matter effects. The other one is not. So you can obviously are free to speculate that it could be difference in non-standard interactions due to the matter effects. But the argument of my talk is this is exactly why we need the next generation of long baseline experiments. More statistics, better understood systematics.
Okay, any other questions? Over here, Diane.
Talking about the current results, or the projections for DUNE. Right. So the projections for DUNE have some implication of that our knowledge of cross sections are going to be improved, and also that some of these techniques of enabling you to disentangle for the oscillation measurement, being able to disentangle the flux in the cross section, it's really going to help you, right? So I suppose right now you have these measurements where you have sort of both of them.
You said the projections assume current uncertainties on the cross sections?
No, those are future, like estimated uncertainties. I can't give you a number though. Yeah.
Okay, especially for students, I'd like to add one more comment here that with DUNE and Hyper-K, we'll be entering an era where we know the mass ordering and precisions on our neutrino masses to the level that we can compare that with against the data from cosmology, like CMB experiment, Bill's leading, or DESI experiment led by also Berkeley, to see if they're consistent with each other, and also have an implication on neutron submobility decay. People in the department are also leading, like Yuri and Gabriel. So this three-way combination is going to be even more interesting, just beyond T2K, Hyper-K and DUNE, but also with cosmology and the nuclear physics. So we're entering a new era. So having said that, what are the opportunities for students?
Oh, there's lots of opportunities to students. Yeah, I think there's DUNE is in a very going as fast as you can possibly can in terms of doing construction, and so it's a really good time and environment for people to be involved in the construction of an experiment. And these things are more rare as times goes by. So I think that's a real plus. And then there's all of these different cool ideas. I think liquid argon is a very beautiful technology to actually observe particles. But here's the challenge: you need to use very modern machine learning techniques to do the reconstruction and do the particle identification. And so you will learn, and we will come up with new ideas about how to include uncertainties, how to do new ways of doing simulation using techniques that are actually pretty useful beyond just the world of particle physics. So that's, I think, another area where definitely people, and particularly junior people, might really enjoy working on, both on the hardware and the construction, but also on the defining an analysis and thinking about how to use modern analysis techniques applied to this technology.
Okay, with that note, let's thank Mary again and for a wonderful talk today.
Thank you. Thanks for having me.